we can use partial fractions to decompose an integral into a simpler form where the degree of the polynomial in the numerator is smaller than that in the denominator. Here we have distinct linear factors in the denominator, so we can rewrite the integrand as follows. Effectively decomposing it into the sum of two constants divided by each separate factor. And now if we multiply through by x minus a by x plus b, we obtain the following expression. And now you can set x equals a, and that'll give you the following equation. And then you can solve for a. And similarly, if you set x is equal to minus b, we get rid of the left term, and we obtain the following equation. Which you can solve for the constant b. And now integrating this sum is much easier than integrating this term. In this case, we have a rational polynomial function where the degree of the polynomial in the numerator is smaller than that in the denominator, but we have a repeated linear factor in the denominator. So we can rewrite this integrand as follows. So effectively we decompose the integrand into the sum of a constant on a distinct linear factor, and for the repeated linear factor we have a constant on the power of each factor. So b on x plus b and c on x plus b squared. And now we can follow the same procedure by multiplying through by the factors in the denominator, so we obtain the following expression. Now if we set x is equal to a, well, this term disappears and so does this term. So what we're left with is ca is equal to a by a plus b squared. And then we can solve for the constant a. And if we set x equal to minus b, well, on the left hand side we get minus cb. And on the right hand side, this term disappears, this term disappears. So what we get is c by minus b minus a. And then we can solve for c. And then you can equate the coefficients of x and obtain b. And once we find those constants, this sum is much easier to integrate than this rational polynomial function over here. We have a rational polynomial function where the degree of the polynomial in the numerator is smaller than that in the denominator, but we have an irreducible quadratic factor in the denominator. So we can use partial fractions to simplify the integrand as follows. And for the irreducible quadratic, we write ax plus b on the irreducible quadratic factor. So as you can see, the degree of the polynomial in the numerator is still smaller than that in the denominator. And then for the distinct linear factor, we add another constant on x plus b. And now if you multiply through by the factors in the denominator, we obtain the following expression. And now if you set x equal to minus b, this term disappears, and we end up with the following expression. And you can solve this for c. And you can equate coefficients to obtain the remaining constants. So I'll leave that for you as an exercise. And then integrating this sum is much easier than integrating this rational polynomial function. Let's evaluate this integral. So the degree of the polynomial in the numerator is smaller than that of the polynomial in the denominator. So we can use partial fractions. And what we have is a repeated linear factor. So we write a on x plus b on x squared. And then plus a distinct linear factor. So we have c on x plus 1. And now if we multiply through by the denominator, we get 3x plus 2 is equal to a by x plus 1 plus b by x plus 1 plus cx squared. And now we can set x equal to minus 1. So that eliminates a and b. So what we get is c is equal to minus 1. And if we set x equal to 0, we eliminate a and c. So what we get is b is equal to 2. And you can obtain c by equating coefficients of x squared. So we have ax squared plus cx squared is equal to 0. So therefore a is equal to minus c, or 1. And now the integral becomes much easier to evaluate in this form.